Hello there and welcome to the second lecture of our second module random events. In today's lecture we will cover set theory and set operations, which is very important in the understanding of the concept of probability theory. So, in this class we will know the concept of set and different sets operation, which will be useful to describe the different probability to different set and subset of a outcome of particular experiment. First, we will know the definition of the set and set theory. Basically, a set is a collection of physical or mathematical objects called as members or elements. So, the elements of a set do not require to have any similarity among them except that they belongs to the same set. So, basically a set, if we want to define that, it is a collection of any a collection of a particular group of elements, and those elements can be physical or mathematical in terms of different outcome of a particular experiment, if we think in the context of our probability theory. Now, this set theory says the theory concerned with those properties of a set which are independent of the particular element belong to the set. So, when we say that set theory, those theories generally applicable to the whole set. It is not related to a particular element of a set. So, the overall the set, what are the different operations that we can do, what are the different theories that is applicable to the full set, and that is we call as set theory. So, with this, if we see that different examples, so if we start with our classical example 1, for example, if we take a coin and if it is tossed twice, then the outcome of this experiment can be of either the first and second both are head, or head tail, or the first one is tail and second one is head, or both are tail. So, the outcome of these events, that is the full all the collections of this experiment is one set. In an experiment is if an experiment is carried out to determine the strength of concrete, in particularly in the civil engineering, then all the experimental values they form a set. In the other example of the stage height, generally we measure the stage height at a river gauging site. There, if we take that the river gauging site, if we take the stage height at a particular gauging site, then the all possible values of the stage height form the set. So, here you can see that these things can have any value depending on the feasible range of the strength of the concrete, depending on various factors, its water cement ratio or the time and type of curing and all these things. It can take any values. For this type of set, this we can say whenever we are saying that is a stage height, this is generally called one side, it is bounded by 0. So, physical or in the mathematically it can take any value starting from 0 to the plus in infinity. So, all this outcome, if we take a total, this is generally, this forms generally a set. There are different properties that we will see now one after another. The first thing is that when we say both the sets are equal. So, two sets are, we generally say these are equal if all the elements of one set belongs to the other set and vice versa. Here in this pictorial representation, there are two sets are there. One is drawn by the red circle and another one is drawn by the black circle. If you see that these are exactly same, so whatever the entries that belongs to the red set, there are some red dots and the black dots, and also there are some so all these dots belongs to both the set S as well as set T. So, now so we can say that this set S and set T are equal. In the example of the throwing a dice, it is having the 6 different output. Now, if I say the one set is even and the outcome is even number, and if in the other words, if I say the outcome consists of 2, 4 and 6, then we can say that these two sets are equal. This is very important, which is known as the subset. A set S is a proper subset of another set, if we can designate that T, when we say that all the elements of this set T belongs to the former one, that is S, but the opposite is not true, that is, which is the vice versa is not correct. So, if you see this pictorial representation, this the bigger ellipse is the T set, and inside this there is another set which is shown in a red circle. So, this S belongs to this T. So, this S is known as the subset of this the larger set T. So, in the example of the river gazing site, if I say that the extreme values of the stage height, then I can say that if I say that all the stage height that is above say 10 meter, or I can say that another set which takes the all possible values. So, the all possible values means that can take any value from 0 to whatever the feasible maximum available height in the historical record, or it can be even higher than that. And another set is that just the extreme value which I put a threshold of the 10 meter, then I can say that the threshold which is more than 10 meter is that subset is a subset of the full set which can take any value from 0 to mathematically plus infinity. The second thing that is known as a null set, when we say that there is a particular set which does not have any element in it, then we say that this is a null set, and it is defined as that when the set contains no element, and this is denoted by this kind of symbol. You can see here that there is a set where there is no elements, then we can say that this is a null set. In the probability concept, we can say that this null set is generally is a set that is the impossible set, there is an impossible outcome. For example, if I say that the strength of concrete, then if I say some value which is negative, then we can say this is an impossible event, and this set is a null set which does not have any entry which belongs to the negative value less than 0. Generally, the sets are classified by its size according to the number of elements that they are having. A set may be finite or infinite. A finite set consists of a whole number of elements which is known as the cardinal number. Now, if any set that is having with the cardinal numbers is called the countable set, and infinite set generally in infinite set, when we cannot count, or the number of elements that belongs to is infinite, or sometimes the another term is used that is called the countably infinite. It can be countable, but it can be infinite in number. Those size of set is known as countably infinite set. So, these are all the basic concept that will be useful to understand the other properties and the operations of set. The second and another important thing is the ordered. If a set is generally said to be ordered if a relation like the greater than or less than can be defined for any two elements of the set. For example, if I take two elements A and B, I can say that A is greater than B or A is less than B is possible, then this kind of set is known as the ordered set. We can even conclude that if we say that A is less than B and B is less than C, then I can say that the element A is less than element C. So, this kind of set is known as the ordered set. These two are two operations which is very important and frequently used. These are known as, one is union and another one is the intersection. These concepts are very important to understand the later part of this class. First we take this union. A union of two events, that is A and B. Here you can see that this is your full set, this is your full sample space, and in this space there are two events. One is this, the left hand side circle, and another one is the right hand side circle, which is denoted as B, and the earlier one denoted as A. So these two are events in the sample space S. Now the union of A and B is generally denoted as A, this symbol B, this is generally read as the A union B. This A union B consists of all the outcomes that is either in A alone or B alone or both in A and B. So you can see these three regions where I am pointing now. This area belongs to A only, this area belongs to the B only, and this in between belongs to both A and B. So if I say that A union B, then this area which is highlighted in red, this area in total is known as the A union B. On the other hand, if I say the intersection, again these two events are defined here, one is A and another one is B, and this intersection is denoted as A, this symbol B, and it is read as the A intersection B. So we call that intersection is defined as all the outcomes those are in both A and B. So it must be both in A and B. So obviously the highlighted area, the red highlighted area, is known as the intersection between A and B. So once again, the union is the total area that consists of either B or A or both A and B, that is the union, and intersection means it is both on A and B. There are other few concepts that is also useful. Here one is the mutually exclusive set. This mutually exclusive set between two events A and B, we can call that this A and B are mutually exclusive when no outcome, no element in A are in B, and of course vice versa. So there is no overlap between these two sets. So if we say that there is no overlap between these two sets, that means if I take the intersection between A and B, now you know this symbol is the intersection, that means in this intersection there is, intersection is a null event where there is no element exist in this part. So you can say that if these two are completely separated, there is no overlap area, these two events known as the mutually exclusive event. In the example of a throwing a die, if I say that one set consists of all the even numbers and another set consists of all the odd numbers, then you can easily say that there is no intersection between these two events, and so all the set consists of the event number and the set consists of the odd number are mutually exclusive sets. There is another very important and very frequently we use the concept which is known as the collectively exhaustive sets. Now the collectively exhaustive sets means when I take some subsets or some events or some sets, and if I take the union of all these events, then I can, if the union of these sets comprise the whole set means that full sample space if it consists of. Now you can see that there are few subsets as defined here. Say for example, this area is your A1, this area is your A2, in this way it is going on, and there are some subsets like this. Ultimately if I take the union, then obviously the full union consists of this whole shaded red shaded area. So this whole red shaded area is nothing but your the full sample space. Here one thing is important to note, that the intersection of any two sets need not be null set. So you can see that this A1 and A2, the intersection is null, but this A1 and if I say that this is another set which is A3, so there are some intersection point. So we are not considering the intersection point here, we are just considering the union. So if I can somehow say that all these unions consist of the full set, then I can say that this is collectively exhaustive set. In the example of throwing a dice, if I say that one event is less than 4 and another event is greater than 2, and if I take the union of these two, obviously the union will consist of all possible outcomes starting from 1 to 6. So the two sets which is that less than 4 and greater than 2, there may be some intersection, but if I take the union of these two, it consists of full possible set. So these two events are mutually exclusive sets. Then the partition of a set. Now this partition of a set, suppose that we have one set in hand and I want to make it partition. Here I just make, this is say the another subset A1, this is A2, and in this way it is going on and up to an. So n numbers of sets are there in such a way that there are two conditions must be satisfied. The first condition is that if I take the union of all the sets, it should consist of the full set, which is here shown as S, the full set. And if I take the intersection of any two sets as long as I is not equal to j, then this intersection AI intersection AJ should be a null set. You see here no events are intersecting each other, so the intersection between any two event, any two subset is the null set. Then we can say that this S is partitioned by A1, A2, A3 up to AN. So a partition U of the set S is the collection of there will be one word of the collection of mutually exclusive and collectively exhaustive. So this is a new word, again we will just explain it in a moment. So the mutually exclusive, this mutually exclusive means all these unions are consist of this full set, again mutually exclusive and collectively exhaustive subset are AIs of the whole set, such that as I told there are two conditions. One is that A1 to A2, if I A1 to AN, if I take the union of all this set, it consists of the full one, and any two set intersection is 0. So in this way, if satisfying these two condition, if we can make the if we subdivide the sets, then this is known as the partition of a set. Now the set operations, there are different set operations. The first thing is the complement. A complement of an set A are the outcome in S, those are not contained in A. So suppose that this is the full sample space A and there is one event A. So this is your event. The complement of A is the area is the set which is not belongs to A. So if I say that the even numbers of throwing a dice experiment, if the even number consists of one event, then the complement of this set is the odd number of the outcome. So one thing is very important to note here is that if I take the union of a set and its complement, then we get the full feasible set, which is S. This complement is generally denoted by either A C or A prime or A bar. So all these notations are, it's just a notational difference, but these are all the meaning are all the same, the complements of a particular set. In this class we will use this concept, which is A bar, to denote that which is the complement of a particular set. Another set operation which falls on this De Morgan's law. Okay, before I go to this, I should tell that these unions and intersections are also the different set operation, which is also very important, that just it is covered, and the complements also covered, and using these two things we will now explain a very important law which is known as the De Morgan's law, and that is very helpful for different kinds of operations on different sets. So this is De Morgan's law. When in a set identity all the subsets are replaced by their complements, all unions by intersection, and all intersections by unions, the identity is preserved. Maybe when I am just telling this one, it may not be very communicable, but we will just explain it what all these things means. Before that, just look at this diagram where there are two sets, one is A and another one is B, and if we just tell once again the recapitulate what just now we have seen. So this is your A, this area is your B. So we know that this is this in between, the intersection between this area which is a little bit gray looking, this is the A intersection B. Here when we write that A B side by side, it indicates that this is the intersection, and when we write this symbol, this is generally the union. So this area is your A intersection B. Now, so if I say this pink area around this one, then it is A complement intersection B complement. So what is A complement here? So whatever the set that you can see here, outside of this area is your A complement, and here it is B, and outside of B is your B complement. Now all this outside area, the outside B, there is a complement B and complement A, if we take the intersection between these two, then only this area where my cursor is moving now, only this area is your A intersection as A complement intersection B complement. Now if I say that A intersection B, that complement, then it consists of this area as well as this area which is not in this intersection, but the rest of this A and rest of this B which is not in this one. So this understanding of these two, that is A complement intersection B complement and A intersection B, that complement is important. So in this A intersection B complement consists of this pink area as well as this A area apart from this intersection, and this B area not belonging to this intersection. So these three area consist of A intersection B complement, and only this outside area which is not in A, not in B, and not in A and B, that is that A complement intersection B complement. Now if we know these three area, then we can just appreciate these two relationship. Just you can see that if A and B are the subsets of a set S, then A union B complement. So A union B complement means this A, first of all we will see where is the A union B. This A union B is nothing but this area, and its complement means this area, what just now I explained, which is nothing but here that A complement intersection B complement. So this relationship we can show it pictorially. Similarly, if I say that A intersection B, then the A intersection B is nothing but only this area. Now if I take the complement of A intersection B, which is shown by this bar here, which is nothing but the summation of three areas. One is that this area plus this area plus this area, and this three area is nothing but your A. So this three area is shown here. Now again, if I see that this one, the A complement union B complement, that is that A outside B outside, if you take the union of this two area, then this three area will be added. So this area plus this area plus this area. So these two relationships also holds good. Now again, I am just reading this De Morgan's law. When in a set identity all the subsets are replaced by their complements, all the unions by their intersection, all the intersection by unions, the identity preserved. So I am just making all the symbols just opposite, in the sense that if I say that intersection is opposite to the union, or the subsets are opposite to their complements, then if I just make this conversion, then this identity preserved. This will be more clear in the next slide when I just see this relationship. This is a demonstration of that what just now we told is that this is your A intersection B union C, and A intersection B union AC. You can even draw another figure just to see that whether these two quantity are same or not. You can see by a simple Venn diagram that these two quantity are same. Now you see this relationship, and you just see the last line first before you go through all these steps. Just see the last line here. Now this A here, this A is replaced by its complement, this intersection is replaced by the union, this B is replaced by its complement, this union is replaced by intersection, this C is replaced by this C complement. Similarly, on the right hand side, this A is replaced by its A complement, intersection is replaced by union, B replaced by B complement. Similarly, this union replaced by this intersection, A by A complement, intersection by union, and C by C complement. So according to the De Morgan's law, if these two are equal, then again these two also will also be equal. Now let us see that in between how we can show this thing. Just in the previous slide we showed that this A intersection B complement is A complement union B complement. So using this one, and we have described this one with this simple Venn diagram, using this relationship here, that A intersection B complement equals to A complement union B complement. If we use this entity and we want to put this one, is that A intersection B union C full complement. So this is one set A, and this is B union C is another set. So this is A corresponds to A here, and B union C corresponds to another set B here. Then using this relationship we can write that this A complement union B union C complement. Again, this in the previous slide, another identity, that A union B complement is equals to A complement intersection B complement. Using this identity, we can even this B union C from this right hand side, we can just write that A complement union B union C. Using this one now this B corresponds to A and C corresponds to B, we can write that A complement union B complement intersection C complement. Similarly, so from this one I just proved that this is equals to this quantity. Similarly, if I use that A intersection B union A intersection C and its complement, this will be equal to, using this identity again, there this A intersection B corresponds to A and A intersection C corresponds to B. Then using this identity I can explain that this is A intersection B its complement intersection A intersection C its complement, which is again equal to, by using this using this identity, A B equals to A complement union B complement, we just put this one here, so that we will get A complement union B complement and A complement union C complement. Now you see this relationship, that is this one is equals to this, and this entity, this set is equals to this entity. Now I have started with the relation that this set, this full set is equals to this full set. So if these two are equal, then their complements are also equal. Now this is nothing but the complement of the left hand side, and this one is nothing but the complement of this one. So if these two are equal, then these two are also equal. So I can write that this entity is equals to this entity. So that way what I can write is that I am just writing this one here and this entity here. So I am finally getting this statement, which if I compare with the first statement, then all the sets are replaced by their complements, all the intersections replaced by their union, all the unions replaced by their intersection, and still we see that if we do all this replacement, then still the identity is preserved. This is what is the De Morgan's law. There is using this De Morgan's law, we can utilize this De Morgan's law for another concept, further to further take this concept which is known as the duality concept, and that duality concept is written here. This is a simple extension of the De Morgan's law. Here this is the S is the full set. So if I say that S is the full set, then if I take its complement, which is nothing but a null set. So S consists of everything. So if I take that its complement, obviously its complement will be the null set, and vice versa. If I take the complement of a null set, then I will get back the full set, which is known as S. Now if in a set identity all the unions are replaced by intersection, all the intersections by their unions, the set S by the null set, and the set and the null set by its set, the full set S, the identity is preserved. So using this, A intersection B, which is equals to this A B, just in the previous slide we have just shown this one, then this will lead to, I will just simply changing this intersection as union and union as intersection on both hands, both side, left hand side and right hand side, then we get the another set, another identity which is also preserved. Then S union A is equals to S, obviously the full set. If I take the union of any subset of this S, then that will also leads to this S, which leads to, if I just replace this whatever I told here, the S by the null set, union by the intersection, and A by this one, then it will return as this S is null set. So you see that the null set intersection A is the null set. So this is known as the duality principle, which is an extension of the De Morgan's law. There are few other concepts also which are also useful in this set operation. Say for example, the first one is the symmetric difference. The symmetric difference for any two sets A and B, the set of elements which exist only one of the set, not in both, called the symmetric set. Here you can see there are two sets. One has shown as the black rectangle, which is denoted as A, and another set is denoted by B, which is a red rectangle. Here there are few elements which are common both in A and B in this area that you can see, and which are not common, which are located in this area or in this area. So now if I prepare another set which consists of all the elements which falls either in A, either in only A and or only in B, then the set that is the symmetric difference between this A and B. The second one is the Cartesian product. For any two sets of events A and B, the set comprised of all possible ordered pair, this is a new term, we will just explain it in a moment. The all possible ordered pair A, B, where A is a member of A and the small b is a member of B set, then this all the possible ordered pair is called the Cartesian product of A and B, and which is denoted as A cross B. Now what is this ordered pair? An ordered pair is a collection of objects having two coordinates such that one can always uniquely determine the object. Thus the first coordinate is A and the second coordinate is B, then the ordered pair is A, B. So always the first entity comes from the first set and the second entity comes from the second set, which is obviously different from the B, A. So if we maintain the first entity of all the sets, all the elements, the first entity always comes from the first set and the second entity always comes from the second set, then this is known as an ordered pair. So once again the Cartesian product, if we see, it states that for any two sets of events A and B, the set comprise all possible ordered pair A comma B, where A is a member of A and B is a member of B, is called the Cartesian product of A and B, which is denoted as A cross B. The third one is the power set. The power set, sometimes this kind of terminologies are used frequently to have the concept, is the power set of any particular set A is a set whose elements are all possible subsets of A. I repeat, the power set of any particular set A is a set whose elements are all possible subsets of A. So if I just take one set, that is 5, 6, then the power set of this particular set can consist either the null set or the one element, the first element, or the second element, or another subset can be consist of the full set, the 5, 6. So there are 4 possible subsets that can happen. So this is known as the power set of this set 5, 6. Generally we say that this any particular set is one subset of its own power set, which is obviously true. There are two more thing that we say, that open set and the closed set. The open set, a set S is called open set if any point A in S always belongs to the set even though it moves to some particular direction. And the closed set, a set is the closed set if its complement is an open set. So the concept of open set is more important, and the closed set we generally say that its complement, if the complement of a set is open set, then that particular set is closed set. Before I go to this example, if simply we say that a particular set that consists of all the integer numbers between 5 to 10, then this is a closed set. And if I say its complement, then it consists of the countably infinite numbers, and that is obviously an open set. Coming back to this particular example, which is taken from the Wikipedia, the point A, B, if they satisfy this relationship, that is a square plus b square equals to r square, which is nothing but an equation of one circle, and which is shown by this blue line here, this circle, then a square plus b square is exactly equal to r square is colored blue here. The points A, B satisfying the a square plus b square less than equal to r square, these are colored red. So there are, this red area consists of many points which satisfies the relationship a square plus b square less than r square, and this circle, this blue circle also consists of many points where it which satisfies this relationship a square plus b square is equal to r square. These red points forms an open set. These red points, what we can see that in between the inside this blue circle, that forms an open set. The union of this red and the this will be blue. The red and the blue points forms a closed set. The union of red and blue points forms the closed set, because if I take the complement of this union, so this union is nothing but this full area, red area including this blue area. If I take the complement of this this set, then it is completely outside. So that is an open set. So that is why this union is a closed set. There is another important concept that is generally say that this is a Borel set. The concept like this, that suppose there are some events, n number of sets, A1, A2, A3 is an infinite sets in some class F. Now if we say that the union of any number of sets here from this A1 to An, or intersections between any two or more than two sets, all these possible cases, all the unions, all the intersections of these sets also belong to the same class F, then the F is known as the Borel field or Borel set. So this is important when we say that we in particularly in the probability theory, when we say that there are some events and which belongs to a class F, whether that probability can be applied to their unions, to their intersection. So to apply that one, this condition must be satisfied, that is that particular set should be a Borel set or a Borel field. Another important thing is the sigma algebra. A sigma algebra is a set S is a non-empty collection of capital sigma here of subsets of S, including S itself. Obviously S is also included, that is closed under complementation and countable unions of its members. So here importantly there are three conditions. One is that set must be non-empty. This is the first condition. Second condition, it should be closed set under its complementation. If I take its complements, then the complements should also be closed, and the countable union of the set also is it is closed under these countable unions also. So there are three conditions for a set. If these three conditions are satisfied, then that set is known as the sigma algebra. So suppose here that this S consists of A, B, C, D is one possible sigma algebra on S, is that this particular set, the null set, first two, second two, and this full set. So this is a possible sigma algebra on the S, where this is your that collection of that particular set. This is a sigma algebra. The probability space. This probability space here is important because that this is the way how we link between the set theory and the probability concept. So, in this probability concept, the sample space S or sigma is called the certain event, its elements, experimental outcome, and its subsets are events. The empty set, null set, is called the impossible event, and the event xi consists of a single element is an elementary event. So, the full sample space or its sigma algebra is a certain event. From the set theory, the full sample space consists of the certain event. Its elements are the experimental outcome. So, in the whatever the experimental outcome that we have taught in the previous classes. So, its elements, the elements of the set is the experimental outcome, and its subsets are corresponds to some events. The empty set, again here if I say some set is empty, that means that is an impossible event. So, for that experimental outcome, that particular outcome is not feasible, is not possible. And obviously, if it consists of a single element, single outcome, that is an elementary event. In the application of the probability theory to the physical problems, its identification of the experimental outcome is not always unique. This is important in the sense that is how you are interpreting the particular outcome of an event that that generally consists of how you are representing that particular outcome. For example, if I say that I am just interested to know whether the outcome of throwing a dice is even number or odd number, then my possible sets or possible outcomes are 2. Either it is even number or it is odd number. But if I say that the whether the outcome is 2, 4 or 6, I am also looking for the even number, but my possible outcome here the 2, 4 and 6. So, there are 3 possible outcome in this representation. Again, if I see that if I throw a die and its coordinate, if I just fix up some coordinate system and say that the outcome is 2 and along with its location where the 2 is comes. So, the location of the die itself, its coordinate, that is x coordinate and y coordinate on a plane obviously, and the outcome is 2. Then the number of possible outcome is infinite. So, this is the way how a particular representation of a particular the application of this probability theory to a physical problems, generally these identifications of the outcome is not unique. The way we want to represent it becomes in that particular way. A single performance of an experiment we generally call is as a trial. So, in a particular trial, whether a particular outcome will come, that depends on this how the experiments is conducted, and that is the way we generally assign the that particular probability. So, a single performance of an experiment is known as a particular trial. In the concluding remarks, in this class we have seen that different set theory, the definition of set, and the set theory that defines the various interrelationship among the elements or the subsets of a set. The set operations also classify the different types of sets, properties of set properties of the elements. So, with this, in the following lecture, in the next lecture, we will explain about the axioms of probability theory, which will be discussed in the next class in details. That will be very important for the probabilistic properties of events and set. Thank you.